Let me share my screen. Are you seeing my screen now? I hope you are seeing my screen. Okay, thank you. Okay, welcome to this second session or second tutorial where we are looking at mainly functions, maybe sequence, and then we need to look at the propositional logic as well as Boolean algebra, something like that. That's what we really want to look at. And let's not forget our basic rules. Let's make sure that we are always on mute. Let's make sure that we are always on mute. If you really want to say something, just raise up your hand. If I fail to pick you, you can just interrupt. There's no problem with that. Okay, so now let's look at functions as our first topic. So normally by the end of this unit, you should be able to describe the concept of functions, represent functions by using graphical representations, also identify different types of functions, right? So let's look at what we call a function is. I hope those people who want to join are being accepted. Thank you for that. So when you look at a function, so a function from a function f, right? Let me just have I think I need a highlighter. Let me just have a highlighter. I want the green one. Okay, so we are saying a function f from x to y is a relation x to y having the following properties. Remember, we have done relations, right? In the previous session, we've talked about relations, and you've seen what is a relation is, and you've seen how these relations will be mapped from the domain to the range, something like that, right? So it must have these following properties for it to be a function. One, or first thing, the domain of f is x. There will be a domain of f, and if xy, where we have x and y, then also we have x and y prime or y, something like that, with this as an element of this function, then y must be equal to this y prime. What does that mean? What it means is that we cannot afford to have maybe x as input and getting y as output, and having the same x as an input and having something which is not y as an output. So whenever that happens, it means that we must have this output that we have, it must be the same as this. So for it to be a function, we are not going to have one value giving us maybe two output from two values as an output from the function, something like that. So a function a function from x to y is sometimes denoted by f, such that x is mapped to y, something like that. So if you if you look at this one, the relation that we have here, we have the input as 1 2 3, or the domain, which is the input there to our function, right? And then we've got this function f here, which is doing the magic, right? So you are saying if you give this function a 1, it's going to do the magic there and give us an a, something like that, right? So we could have this 2, then give us a b, this 3 give us an a, right? So this f will be a function which is taking the input, which is this domain, and give us the output, which is this range, something like that. So that's what we call a function. So let's talk about what we call the domain and a range to a function, right? So the domain of f is x, right? Or a domain of function f is x, and the range of f is a b. What does this mean now when we are talking of the domain being x and the range being a b? So the range of a relation R is the set y is an element of what, such that xy is an element of our relation for some x is an element of x. What does this mean? Whenever you get this xy as part of your relation or as part of your function there. What it means is that this x will be belonging to this set of x, or this is set of values that we are giving to our function, which is the domain. That's what we call the domain. And this y will be belonging to the range, which is the set of values that we get after putting the values from the domain, right? So take the domain as the set of values that we can give to a function, and take the range is the output that we get after putting or after giving a value to a function. Just like what we have here, you can give a function a 1 and it gives you an a. So 1 is part of the domain, so it's part of the set that we're talking about of the domain, and then this a is part of the what of the range, something like that. So that's what we'll be talking about. So we've got this function that we have here, f of x is equals to x squared, and this relation is a function, and the domain is the set of all real numbers. Why that? Because you can give any real number that you want to this and you can still get your output, something like that. So that will be your domain, right? But what if you've got maybe 1 over x there, which means we cannot afford to have an x there as a 0, which means as part of your domain we do not want to see 0 there. Why? Because if you put a 0, 1 over 0, it's undefined, something like that. So basically that's how we look at the issue of domain and the issue of what of range. Then let's talk more about these functions, right? So we've got this example, which of the relations define functions. From x we've got 2, 4, 5, and y, which is 1, 2, 4, 6. So what it means is that we've got this as our domain and this as our range. If you put a 2, whatever we must get a value which is within this, which is 1, 2, 4, 5, 1, 2, 4, 6. And if you put a 2, you must get any value, something like that. So we are being asked which of these qualifies to be a function. So we are looking at these basics that we have been talking about here, that we cannot afford to have 1x, the value of x giving us 2 different values, something like that. So we are looking at these requirements for it to become a function, right? So now we look at what we have here is R1. We've got 2 from the domain, which is fine, and then we've got a 4, which is fine because it's there on the range, and then we get a 4 as our input there. It's okay, it's there, but we've got a 1 as an output there, yes, which is okay. Then now let's look at it. Is this a function? Is this a function? It's not a function. Why is it not a function? If you look at it, we've got 5 in the domain, but this 5 is not part of this, right? Something like that. So if you look at it, so we were supposed to, so all the set or all the values that we have in the domain must be able to fit in your what? In your function and give the output which is acceptable, something like that. So R1 is not a function because 5 is an element of x, does not appear as the first element in any ordered pair in R1. So anything that we have in the domain must be able to fit in our function and give us the output that we want. As simple as that. I think it makes sense. So R2 is R2 a function. Let's look at it. We've got 2 from the domain and a 4 from the output, which is fine. We've got a 4 from the domain and a 1 from the yes, which is good. And then again, not again, but we've got a 4 here, which is yes, it's again, we've got a 4 which is the same value, right, from the domain, this 4 again, and it's giving us the output as 2, which is not the same as this one that we have. So whenever you see that, it means that that relation is not a function at all. Why? Because we've got the same, or we've got one value giving us 2 different output. Does that make sense? So that one, it's not a function. We cannot rely with that. You are giving it one value, it's giving you different values. right? So that one will not qualify as a what, as a function, unless if we try to restrict the domain to make it a function. You can have something which is not a function if you restrict the domain to say that maybe you give a condition and then maybe to become a function. But for this one, it's not a function. It's taking one value, giving us two outputs. And then let's look at the R3 there, the relation R3. If you look at it, we've got 2, 4, which is 2, and a 4 here, and then we've got this 4, this one, and a 1, which is this one, and then we've got a 5, this, and a 6 from here. So this one qualifies to be a relation because we do not have the scenario where you have maybe one value from the domain giving you multiple values here. So this one qualifies or defines a function because it satisfies both the conditions of the function, that is every element of x is the first element of some ordered pair, and there is no pair which has the same first order pair but different second order pair. So let's look at what we call the graph, right? The graph of a function. I think this one you have been doing it when at O level you've been drawing the curve, whatever, the graphs, whatever of any given function. You've been doing this, drawing straight lines, whatever, all those things. So normally what happens to the graph of a function whenever you want to draw it, I think it's very, very simple. We've been doing this where you put it on a Cartesian plane. You just need to have the values of x and the corresponding values of y, and then you plot and then you draw something like that. It's just the same concept that we are talking about, right? So let f be a real valued function of a real variable, that is f is such that r, or the r is mapped to r from real value to real value, something like that. So the graph of f is the set of all points xy in the Cartesian coordinate plane with the property that x is in the domain of f and y is equals to f of x, right? So x will be the domain, and then y will be the output that we get after putting the value of x. Like here, when you say f of x, you are just putting the value of x and then you replace it on the function, whatever. So we have to draw the graph of the function f given the relation y is equals to x squared. So the relation is y is equals to x squared. So in order to draw the graph of the function, we will first take some elements from the domain, and then we see the image of them and then plot on the graph. So if you look at it, so we are just choosing to have -3, -2, -1, 0, 1, 2, 3, something like that. So you can also choose to take any other numbers that you really want to take, and then you plot, right? So here we are looking at if x is equals to -3, so substitute here. So -3 squared it will give you a 9, -2 squared to give you a 4, -1 squared to give you 1, 0 squared a 0, 1 squared a 1, 2 squared a 4, and then 3 squared it will give you a 9 there. And then you draw, you put your scale, whatever, and then you start to plot when x, so this is x, this is y, right? So you plot when x is 1, 1, whatever, something like that. So you start with the x -3 and the y be 9 there. So you go for -3 and 9. So this is here. So here it's -3, and then this is your 9 there. So you plot here. So you plot, you plot, you plot, you plot, you plot, then you draw that curve, because this is a curve. So that's how we come up with a graph of any given function there. So now here we want to talk about the types of functions. This is the very, very important part as well of functions when it comes to what we are doing here, which is mathematical foundation, right? So when we are talking of these types of functions, we'll be talking about injective, surjective, and bijective, right? You need to know what is injective function, what is a surjective function, what is a bijective function. It's very, very easy to know that, and it's very, very simple and very cool. But I know it happens that sometimes it confuses us, right? So let's look at so now let's look at this, right? The injective function. Let's look at the injective function. So by definition, a function of a function f from x to y is said to be 1 to 1 or an injective if for each y is an element of y, there is at most one x is an element of x. So when we say at most, take this word, excuse me, at most means less than or equal to 1. That's the at most there, at most. Also, by just saying a one-to-one function, it means whenever you give any value to a function, you must get a single value as output. So that alone tells you that what is an injective function, right? So the condition given in the definition above for a function to be one-to-one is equivalent to if x and x prime, like if you have an x here and is something like another x prime or whatever, let's say maybe it's a and b, so these two things are different, is element of x, and f of x must be equal to f of x prime, right? And then not must, but if f of x is equal to f of x prime, then it means that x must be equal to x prime. So we are just saying if you have a and b as part of the domain, right? And if you, by any chance, if you get f of a being equal to the value of f of b, like if you put a to the function and put b to the function and get the same result, it means that a and b is just one value. That's what we are talking about as the what? As an injective function, right? So if you look at it like this one that we have here, whenever you are putting a 1 to a function, you are getting one value, 2 you are getting a 1 value there, 3 you are getting an a there. There is no possibility of maybe having something like this, and by doing so it's no longer a function as well, because this 3 is giving us more than one value, something like that. So we are saying one value is giving us one output, something like that. So this side we must only see one arrow coming to the elements which are in the what, in the range, something like that. So that's how we get, or that's how we see that this is an injective function, right? So please, if you really need any clarification there, it's good to do ask, right? To ask if there is any need of clarification. But that's what we call an injective function. So how do you see that this is an injective function? By just looking at a graph, right? The graph of a one-to-one function or an injective function. So a graph of a function f is one-to-one if and only if this IFF is if and only if every horizontal line intersects the graph in at most one point, right? So you must only, if you draw a horizontal line, it must cut the graph at only one point. That shows that whenever you are putting one value there, you get a corresponding single value there, right? It's different from this, right, where you put this value, if you cut, right, so this one will cross the function, you cut the function twice, right? This one, so if you put -2 you get the same value, if you put it 2 you get the same value. We do not want that. Why? Because of the at most part that we are saying here, the at most part, this one, which says there is at most x is an element of x with f of x is equal to y. So here we must not have two arrows pointing to any of the elements here. Okay, now let's talk about what we call a surjective function or an onto function. So if f is a function from x to y and the range of f is y, f is said to be an onto y or an onto function or a surjective function. So the function from x to y is onto each element in y in its arrow diagram. So in its arrow diagram we have at least one arrow pointing to it. So when you say at least, which means it's more than or equal to 1, right? So if you have something like this, it means this one will not be able to be a surjective function or an onto function. Why? Because this t has nothing mapping it to there's nothing mapping to this D. So we need to have at least one item being mapped to these things that we have for it to become an onto function or to become a surjective. So if you look at it by looking at this, every value in the range have got its input. So by doing so, this will become a what? A surjective, right? So that's what it is. We can have another value here, maybe pointing to see it's acceptable there. These are different values giving us the same output, and it's acceptable, and it will be still a surjective function. Why? Because it will be at least more than one, right? At least, which is greater than or equal to one. So the graph of an onto function or a surjective, so a graph of a function f is onto if and only if every horizontal line intersects the graph in at least 1 point. So it needs to intersect the graph at least 1 point, right? So whenever you are drawing this, so if you are saying at least, this is at least 1 point, right? It needs to cross this line at least 1 point. Then there's what we call a bijective or a one-to-one correspondence. So a bijective from bi, it means that this is now we call it what? Both surjective and both injective function. So that's why it is bijective function. So a function f such that x maps to y defined by the arrow diagram is both one-to-one and onto, hence it's a bijective function. Why is it one-to-one? Because here we've got at most, which is less than or equal to 1, right? So a is mapping to this, b is mapping to this, c is mapping to this. So there are no two mappings here, like maybe two arrows. Maybe if we have got maybe a d here mapping to 1, which means you're going to have two like having two values from the domain mapping to one item. So since we do not have that, so this will become a bijective. Why? Because we've got at most and at least 1, right? So it satisfies both the injective and the surjective. But if we're going to have maybe here a 5 as value in the range and nothing is pointing to it, then this cannot qualify to become a what? A bijective function, because for it to be a bijective, it must both injective and surjective. So this one will be an injective function, not a surjective function. Why? Because we will say at least one value from domain must be mapping to this whatever output, but here this 5 will be mapped to nothing. Okay, so is it a contribution or a question? Let's make sure that we are all on mute, unless if you want to say something. So basically that's the bijective, that's the bijective there. So a graph of a function f is bijective if and only if every horizontal line intersects the graph at exactly 1 point. Why? Because remember I said it must be both bijective and both injective, just like that. Maybe what do we need to look at? The inverse of a function. The inverse is whenever you want to, maybe you are given a function, right? You are asked to find its inverse. So when you're looking at the inverse of a function, it's as good as you want to go maybe from the image to the actual input, something like that. That's the inverse there of a function, right? Like whenever you have a domain and a range, so when you give the value from the domain, you get a range. So when it becomes the inverse, the range will become the domain, something like that. So you'll be giving it what you have in the range and get what you have in the domain. So let f be a one-to-one correspondence from the set A to the set b. So the inverse function of f is the function that assigns to an element b belong to b the unique element a in a such that f of a will be equal to b. So it's as good as we are reversing it. So the inverse function of f is denoted by this f to the power minus 1. So here's the inverse f of which is f to the power minus 1, which is the inverse of f of b, will be equal to a, which is when f of a is equal to b. So in other words, we're just saying if you put a in the function, you get a b. And then if now it is the inverse, if you put b in the inverse, you must get this value, which is a. So it's as good as you're just interchanging, something like that. So that's what we call the inverse there. You can look around it, but I don't think there's much of interest here that we need to really talk about. Maybe we need to talk about the function composition, but this function composition, we really looked at it yesterday. This one, the function composition, when you talk about the transitive, all those things, the relation composition, we talk about that. Only that when you're talking of a relation, some relations are functions and some are not, but otherwise it is the same concept. So what I'm going to do is I'm going to look at this. Let's look at this one. I have this website that I've just put here, which talks about the composite functions, right? So normally if you look at it, it's just like what we have been doing yesterday. If you look at it, we've got a and b and c, right? So if you put the values of a into this function, you get this b whatever, and if you put this b to function g, you get this value that you have at c. So a now is mapped to c through this function composition, something like that. This is what we have been covering yesterday. So let a implies b, and let f be a function such that a is being mapped to what, to b, and the g be a function such that b is being mapped to what, to c. So b2 functions. So then the compositions of f and g denoted by g at f or g of f, something like that, is defined as the function g at f. A implies what? Implies c, or a is mapped to what? To c, something like that, given by this g at f of x, or you can write it this way, right? So if you see this g with this circular, not a dot, if it is a dot, is a product. You are multiplying two functions, right? But here you are taking this f as an input to function g, and then you get the output, something like that. So maybe you can look at where there is an example of that, like here, if f of x is equals to 3x plus 1 and g of x is x squared, then f of g of x, or f at g of x, something like that, will be equal to f of g of x. So you put g of x everywhere where there is an x in f of x, something like that. Like if you say f of 2, you just replace this x by what? By 2, because you have got an x. So f of 2, you replace this x by 2, so it will be 3 times 2 plus 1, which will be 7, something like that. So here you are just taking this g of x, which is x squared, and then replace every x in f of x with what? With this x squared, something like that. So that's why we've got f of x squared, which is equals to, now you replace this x with x squared, so you get this x, so it will be 3x squared plus 1, something like that. So that's how you really go around with this. Maybe the next thing that you need to do is to be able to add the functions, right? Like here, what is f of x plus g of x? It will be just x squared plus 3x plus 1. Even if you want to subtract maybe g of x minus f of x, to be x squared minus 3x plus 1. If there is need of maybe simplifying it, you can simplify it, right? Maybe like, what if this one's not x squared, is just x, right? So it will be, maybe if you want to say f of x plus g of x, so it will be 3x plus 1 plus x, so it will be 4x plus 1, something like that. So that's how you do operations on functions, right? multiplication is just like what you used to do when you expand, whenever you do algebra, what is something like that. When you be adding, multiplying, something like that, that's what you do. So basically, I think that's all on functions. If there are any questions, you could ask, but that's really all about functions. Otherwise, we really need to look at maybe sequences. We really need to look at the sequences. So for now, maybe I'll be waiting for questions if there are questions. But if there are no questions, what I will do is to have this, which is sequences, right? Let's talk about sequences. So I want to talk about sequences. So normally when we talk about there's what we call sequences and strings, right? Sequences and strings. So by the end of this unit, you should be able to describe the concept of sequences, operations on sequences, maybe to discuss the concept of strings and operations on strings as well. Okay, so normally when you talk of sequences, right, you are talking of an ordered list, right? If you have got an ordered list or set of ordered list, whatever, something like that, then that thing become a sequence, right? There's an order there that we really need to follow, right? So that thing will end up giving us what we call a sequence. So a sequence whose smallest index or the smallest value is what is one is a function whose domain is either the set of all positive integers or a set of the form 1 2 3 blah 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 up to n, something like that. So if S is a sequence, we denote the first element is S1, but not S1 like this, S1 with the subscript 1 here, something like this, S1 like this. And the second term is S2 like this, S2. And maybe the third term is S3 up to the nth term. So that nth term, it will be Sn with this n, something like that. So that's the notation that we normally use when we are doing sequences. So you might be asked to find the nth term, right? Something like that, which will be like Sn. So the order the list 2 4 6 up to 2n is a sequence, right? So the first element is 2 and the second element is 4 and so on, right? So the nth element is 2n. Whenever you want to find what you call the nth element, someone was saying hi on hi on YouTube. Okay, I'm seeing you. I'm good. Okay, so um I was saying that the nth element, right? It's any element that we want which is in our sequence. If we want the fifth element, we put 5 there, right? If we want the 10th element, we put a 10 there on n, right? So this will be Sn. That's what I've got. And the formula to find the nth element is 2n. Why? Because the first term is 2. The second term is 4. So it's like 2, 4, 6, whatever. So these are multiples of what? Of 2. So if you want this second element, which is 4, you can just put a 2 here. So it will be 2 times 2, then you get a 4. The third one, which is S3. So n will be equal to 3. 2 times 3 is 6, something like that. So if you want the 10th element, you just put it will be S10. So it will be 2 times 10, so you get a 20. So that's the 10th element, something like that. So normally that's how we work with these sequences. I think it's simple and clear there. Then let's look at this one that we have, which say Munenzo buses charges $1 there for the first kilometer, right? So for every first kilometer, we charge $1 and 50 cents for each additional kilometer. What does this mean? It's $1 for the first kilometer, but any additional kilometer that comes next, we charge 50 cents. So in general, the cost Cn, if you want to find any nth element, like what if it's 200 kilometers, well, what's the price? So we want the formula to find the nth element, right? So Cn of traveling, let me take my highlighter there. Okay, so if you now look at it, the cost cn is n is the subscript n there, of traveling any kilometers is given by 1, which is the cost of traveling the first kilometer, plus 50 cents, which is half of a dollar, so it's 0.5 or half, times the number of additional kilometers, which is n minus 1, something like that. So how does this formula work here? Why dollar plus 0.5 times n minus 1? What we want to do is, the first kilometer we know it's a dollar, so the second kilometer it's no longer a dollar, it's a 50 cents. The third kilometer it's no longer a dollar, it's a 50 cents, right? So if you look at it, n minus 1, which means we want to say for the total number of kilometers that we have here as n, we want to subtract 1 kilometer. Why? Because this one that we have here is representing the price for that kilometer, and the rest we multiply by 50 cents, and then we add to this dollar, and then we get the output, something like that, right? So if you look at the first kilometer there, it will be 1 plus 0.5 times 1 minus 1, which is going to be 0.5 times 0, which is going to be a 0, so we just left with a dollar. For the second one, it will be 1 plus 0.5 times 2 minus 1, which is 0.5 times 1 there, so it will be 1 plus 0.5, which is $50. So if you look at that, this formula now can generate any nth term that we want, right? So we call it the nth term, right? So that's how this works, right, when it comes to sequences and strings. Okay, so the list of phase in the example above is in a sequence, and a sequence can have repetitions as well. So there are there are types of sequences, which are the decreasing sequence and increasing sequence. I think from the name, it's just what it is. If it is a decreasing sequence, you are starting from the higher number, they going down, right? So maybe the previous number is bigger than the next number, something like that. That's the decreasing sequence. But in an increasing sequence, you are starting from the smaller number going up, something like that. So that's what it is. So in an increasing sequence, is such that Sn is always less than or equal to Sn plus 1, which means the previous number or the previous term, we call them terms, right? We call them terms. So the previous term is always less than or equal to the next term. So that will be an increasing sequence, like 2, 4, 6. Then what about the decreasing sequence? I think that this one, which is 2, 1 half, 1 over 4, something like that. So as you see that the previous term will be always greater than or equal to the next term, something like that. Then let's talk about a subsequence, right? A subsequence is just like whenever you have a sequence, you can take a subsequence or take a part of that sequence, something like that. So we are giving that we are going to start it here and end it here, right? So let Sn be a sequence defined for n is equals to m plus 1 and let n1 n2 be an increasing sequence satisfying nk plus 1 for OK, so whose values are in the set m plus 1 So we call the sequence S of nk as subsequence of Sn. What does this mean? So the sequence BC is a subsequence of A, B, C, Q. So in short, this whole mathematical definition that can crack your head is trying to explain to you that you can take this part here as your subsequence, like this BC, a subsequence. Maybe you can take this ABC, a subsequence of the entire sequence that we have. So notice that the sequence CB is not a subsequence of the sequence of this sequence. You cannot have CB as the subsequence. Why? Because now it's not in the direction that we're supposed to. This is the first, the second, the third, the whatever, the nth term, just like that. So you cannot take Q, C and say it's a subsequence of A, B, C, Q. It's wrong. So the sequence 2, 4, 8, 16 this one that we have is a subsequence of this whole sequence that we have, something like that. So we can talk of what we call the sequence operations, right? So if you look at what do we have here? The summation from I is equals to m up to n. So this is just the summation of a given sequence, right? With the summation of a given sequence, which will be from starting from I is equals to m up to I is equal to n. So you'll be summing those or each and every item that we have in our sequence. I think we will to see this normally when we are talking about geometric and AP arithmetic progression. Normally that's when we apply these things, right? But in general, whenever you want to do the summation uh, of um, of terms, right? The summation of terms in a sequence, you could do so like here. This what we have here, it's just this one, the sigma here, this one, it's a summation from I is equal to, which is the lower limit, it is the upper limit, up to n, right? So you'll be saying m and the next term a m plus 1, the next term up to a n, which is this, the maximum value that we have there, or the maximum index. So it is good we are saying it will be, if it is the summation of a sequence, it will be maybe 2 plus 4 plus 8 plus 6. So you'll be taking the first term, adding the second term to the result, whatever, adding whatever, something like that, till to the last, or till to the nth term, this one. And then for the product, you just multiply, like here it will be 2 times 4 times 8 times 16, whatever, going till to the nth term, something like that. So normally that's how it is done. And this was just an example here, which says let a sequence be defined by an is equals to 2n is greater than or equal to, where n is a number which is always greater than or equal to 1. Then the summation from I is equals to 1 up to I is equal to 3, which means we are going to take the first term up to the third term. So the first thing is to know what is the first term, what is the second term, what is the third term. So you put you put your I there as 1, and then you get a 2, and then you put your I as 2, you get a 4, you put your I as 3, you get a 6, and then you add all those elements, whatever, or terms, and then you get the result. You do the same with the multiplication, right? Maybe what do we need to look at? Maybe let's look at what we call strings, right? There's what you call a string. We've been working with the strings in programming, and then let's look at what is this thing that we call a string, right? So a string over x is a finite sequence of elements from x. So normally a string is formed from these sequences. All right, so let x be a b c. So if we let q1 be equal to b, and q2 be equal to a, excuse me, and q3 be equal to a, and q4 be equal to c, we will obtain a string over x, and this string is written as q1 q2 q3 q4 as b a c. So we are saying if we let this first term, or this first part of our string be b, then this one be a, then this one be a, and then, so what we form is this string, right? So that will be our string there, which will be BAAC, something like that. So the definition of a string there, we let this x star, or this with the asterisk, this one denotes the string of all strings over x. Like we are talking of all the strings that we can generate over what? Over the set x that we have, including the now string or the empty string, something like that. And we let x plus denotes the set of all non-now strings over x. So if you are being asked to find this, or to come up with this, we are talking about all the possible strings that we can create, including the empty, like what you used to do when you are looking at the power set, something like that, where we'll say the empty set is part of the something like that. So that's what we are talking about. But if it is x plus, we are discarding that empty set or that part that which is a null string, right? So the string with no element is called the null string and is denoted by this lambda, this one, this sign. So let x be a b and some elements in x star are what? We represent the null string as this, and then since we've got a b, so we can take a alone, we can take b alone, and then we can take maybe a b, whatever. We can take maybe b to the power 20, which is b up to something like that. So these are some of the strings that we can form from this a b, right? So the length of a string is normally represented by this alpha, this one. So we put a modulus there to say the length of a given string, something like that. So you can also say here, when you have a to the power 5, you can even write as a whatever, or you can just say a to the power 5, something like that. So there's this example again that we have, which says that if this alpha or whatever is or this string is a b, and this beta is equal to this, then the length of this one is 5. Why? Because it's 1 2 3 4 5, something like that. And the length of beta, it will be 39. Why? 8 32 and this 4 and this 3. Why? Because we've got these a's, 3 a's, 4 b's and 32 a's, something like that. So you just add them just like that to get this length of a what? Of a string. So if this alpha and beta, there are two strings, then the strings consist of alpha followed by beta, written as alpha then beta, some sort of like you are concatenating, we call it concatenation of a string, right? In programming, that's what we used to say, concatenation of strings, or you are joining those two strings, right? So how do you join them? Something like that. So if T is AAB and E is CABD, then TE, which is concatenation of a string, will become AAB CABD. You just take this and join it with this, right? So you can even write it as A squared BCABD. There's no problem. So if it is ET, we are starting with this CABD, then AAB, something like that. Then if you say T, then joining it with the now string, the this one, it will remain as AAB, and this one always will remain as AAB. So that's it on sequences in the strings. But we really need to look at one thing before I close this chapter on the strings, which is the issue of arithmetic. On the sequences, we've got two types of we've got those types of the arithmetic progression and the geometric sequences. So we need to look at this, like what are these things, right? What are these things? The arithmetic progression. What are these things that we call arithmetic progression, or AP, right? I think you've been seeing it in your assignments, whatever. So let's talk about this, right? So by definition, whatever, this you are looking at just at a sequence, right? And then the difference between successive terms, like the first term, second term, third term, whatever, those successive terms is so the difference between those is what is constant, right? So this means that at each step a constant value is being added to each term of this sequence. So maybe if I say I've got like here I've got 1 3 5 7, so if you look at it, I'm adding a 2 to 1 to get 3, and I'm adding a 2 to 3 to get a 5, I'm adding a 2 here to get a 7. So it's as good as the next term that we are getting is after we add a constant number there, what we call D, or the common difference, right? So that's what it is then. So there are some of the formulas now which will be derived from this type of sequence that we have, where we say that each and every next term will be derived from adding a constant number there to the previous term, something like that. So there was a formula that was driving there to help you to solve that, right? So normally when you talk of an arithmetic progression, what happens is that the first term we call it A, right? So the first term is A, so this one will be our A, right? And then how do we find the next term? Normally you can say A plus D, right? The common difference. So there's what we call a common difference, which is going to be D, right? So whenever you see a D on the formula that is to do with the arithmetic progression, not that this is a common difference, or the constant that we are saying is the one that we are adding. Like here, our D is 2, the common difference, so we are adding 2 as our D there, something like that. So here we'll be having A plus D as the second term. The third term, it will be A plus 2D. The next term, it will be A plus 3D. Why is saying so? If you look at it, this one, if you look at it, the second term, right, it will the first term is 1, right? The second term is 3, which is A, the first term, plus D, which is the common reference, which is 2. So we are saying A plus D, which is 1 plus 2 to get a 3, something like that. And if you want this, which is this 5 that we have here, what do you do? Which will be A plus 2D, which will be 1 plus 2 times 2, which is 1 plus 4 to get a 5. So if you want this, it will be A, which is 1 plus 3 times 2, which is 6 plus 1 to get a 7. So that's how we do. So there's a formula there which will give you what we call the nth term for an arithmetic progression. So the formulas that you want normally are these first two, or this one with the last one. But normally this one only works when you're given the last term. If you're not given the last term, then you need this and this. That's what you need there. Okay, so what is this an? An is just represent the nth term, any term that we want to pick on our sequence, just like that, right? And then a1, it means that this is the first term, right? And then plus n minus 1, n is the nth term that we want to look at, and then d is the common difference. So we'll be saying, if you want to look for this, which is the second term, so it will be a2 here. So it will be a plus 2 minus 1, then times d. Our a is 1, 2 minus 1 is just 1, so it will be 1 plus d, which is 1 plus 2, which is going to give us 3. So this formula will generate the nth term, like what we used to do when we have done the sequences there. I think we've generated the formula when you talk about Monenzo of the price is what this is what we have generated. So this is the thing that gives you any term that you want to have, right? So for this one, if you want to find the total sum, like the summation that we've been talking about, so if you want to find the total sum up to certain numbers, like here I want to find the total sum of these 1 2 3 4. Okay, so I want to find the sum, or S4, the sum to 4 numbers, or the sum to 4 terms in this arithmetic progression, which is 1 plus 3 plus 5 plus 7. What is this? 10, 15, 16. All right, so what do you do? It will be sum of 4, so it will be S4. So it will be n is the nth term, whatever that you are talking about. So it will be 4 over 2, then in square brackets 2a. What is your a? Your a is 1 there, because a is the first term. What is the n? N will be 4 again, minus 1, then times d. What is d? The common difference 2. So you are talking about 4 over 2 to give you a 2 there, right, times 2a, which is a 2 again. It's just a 2 because this is 1, then plus n minus, so this will be 3 times d, 3 times d, which is 3 times, which will be a 6. So it will be 6 plus 2 to give you an 8. So it will be 8 times 2 to give you a 16. So that's what we have computed here and get. So this formula gives you the sum to up to n number, or sum to n. We call it sum to n, right? So it's sum of any terms of an AP, just like that. Then you can use this if you have got the last term. right? That one, like here we've got 7, so we say 7 is the last term. That, so you will be saying that n over 2 times a plus the last term, something like that. So we say here we are looking at S4, right? So it will be 4 over 2 times a plus the last term. So it will be 7 plus 1, which is 8. Then 2 times 8, it will give you 16. So this only works when you're given the last term. So sometimes you might not be given the last term. So that's it on the arithmetic progression. Then there's what we call the geometric progression. So the geometric progression is just almost the same with the AP, but only that this one now the numbers are no longer increasing by a constant, but now we are using a factor here. Like we are multiplying with the what? With the factor to our numbers, something like that. So you have here is 2, 4, 6, 8. It is clear here that each term is being multiplied by what? By 2. So in this sequence, such sequence where successive terms are multiplied by a constant number are called geometric progressions. So in a more general way, a sequence a1, a2, a3 up to an can be called a geometric progression if an plus 1 is equals to an times r, and where n is any natural number. In such series, a1 is called the first term, and the constant term r is called the common ratio. Call it the common ratio. So if you look at it here, we've got the d, right, the common difference, but here we've got what we call a common ratio. So you need to know how to find the common ratio. Here we're saying this minus this to find sorry, we're saying this minus this, this minus this, whatever, the next term minus the previous term, the next term minus the previous term, to find the common difference, right? But here we need to find the common ratio. Common ratio will be saying this divided by this, so it will be like the next term divided by the previous term. So if you say 16 divided by 8, you get a 2. 8 divided by 4, you get a 2. 4 divided by 2, you get a 2. So that one will be the common ratio. So it just for you to confirm, is this an AP or is this a geometric progression? Pick these two consecutive numbers and the other consecutive numbers, do the subtraction there or do the division, and then you will see that are you getting a constant number. So if you say 16 minus 8, you get 16 minus 8, you get a 8. You say 8 minus 4, you get a 4. So this one is automatically, it's not an arithmetic progression. But if you say 16 divided by 8, you get a 2. 8 divided by 4, you get a 2. So this one now satisfies the geometric progression. So the next thing is to work with the formulas for geometric progression. So how do you find the nth term of a geometric progression? Use so this is the formula to find the nth term. This one, so this one, right? So this one is saying the first term is a, so the second term it will be a times r, which is the common ratio. So the next you say a times r to the power 2 up to n. So the formula that you use is an is equals to a times r to the power n minus 1, right? So if you want the third term, you say a times r to the power 3 minus 1, which is a r to the power 2, something like that. So if I want to find the third term, which is 8, and I know that the common ratio here is what is 2, so it will be a times 2 to the power 2. So it will be 2 times 2 squared, which is 2 squared is 4, so 2 times 4 is 8, so you get this, something like that. So if, for the summation, the sum to n, what do you do? This is the formula. It will be a times 1 minus r to the power n over 1 minus r. You do what we do with the AP there. A is the first term, and then r is the common ratio, n is the nth term that we are talking about. So if you want to do the sum up to 10, so your n here will be 10, something like that, up to 10 terms, so your n will be 10. I don't know if there are questions here or contributions. Otherwise, that's all on sequences. Otherwise, that's all on sequences. I'll be waiting for questions as I move to the issue of the propositional logic. The propositional logic, which is a very, very important topic that we really need to familiarize ourselves with, and to take it seriously, and to read this slide is there on your portal. I think I've said it a lot of time that if you're on the portal, it's a must read, right? So it's something that you really need to read for you to get an understanding of this. So guys, if you really need to ask a question, please do ask, right? I hope I'm audible. So please do ask if you really need to ask a question. It's very, very important. So by the end of this unit, you should be able to explain the concept of propositions, apply apply operations on propositions by using the truth tables. So what I will do is I will look at the propositional logic, but at the same time I will try to ask questions so that it will be interactive. I hate it when I'm just talking and talking and talking. I feel like I'm talking to myself. But I'll try to make it interesting there. Okay, so let's talk about this thing that we call propositional logic. So in developing a mathematical theory, assertions or statements are made, right? For you to say for this mathematical theory, normally there are assertions or statements that we need to make. And these statements are made in the form of sentences using words, mathematical symbols, and when proving a theory, a mathematician uses what we call the system of logic. We need to see the logic. We need to see clearly step by step. So this is also the case when developing an algorithm for a program or a system of programs in computer science. So the system of logic is applied to decide if a statement follows from or is a logical consequence of one or more other statements, right? So let's look at what we call a logic, or what is this thing that we call a logic, right? So logic is the study of the principles and the methods that distinguish between a valid and an invalid argument. So we have arguments there. Which one is valid? Which one is invalid, right? So logic is the basis of all mathematical reasoning and of all automated reasoning. So it is practical applications, like if you can use it in the design of computer machines, to the specific specification of systems, to artificial intelligence, to computer programming, to computer programming languages, and maybe other areas of computer science, as well as to many other fields of study, right? So now let's talk of what we call a statement. This is something which is very, very important, right? What we call a statement. What is this thing that we call a statement? So normally a statement is an assertion or a declarative sentence that is either true or false, but it cannot be both. So normally we might have a sentence there, but that sentence, for it to become a statement, it must be either true or false, right? But it cannot be both. So we cannot have a statement which is both true or false. So if you say something, if you say any statement in there, it is either true or false, but it cannot be both. So a statement is also referred to as a proposition. So when we say propositional logic, a proposition is a statement. So if you see something asking about a proposition, you are being asked about a statement, and that statement is the one that we are saying it can be a statement if it is only having a truth value, true or false, right? So the truth value of a mathematical statement can be determined by application of known rules, axioms, and laws of mathematics. So a statement which is true requires a proof. You cannot say that this statement is true without proving it. So it requires a proof. So for example, 2 plus 2 is equal to 4. This one is a statement because we can prove it that 2 plus 2 is equal to 4. And you can even disprove it if you really, or if you are able to disprove it. It is Sunday today. We can prove it, right? Is it Sunday today? No, today it's Wednesday. So this is a statement, but this statement is a truth value of false, or it is false that today is what? Is a Sunday, right? So that's how we make our statements there, and that's how you find their truth values. What are their truth values? Something like that. So if a proposition is true, its truth value is true, or you can put a 1 there. Normally other textbooks use a 1, other textbooks use true there, right? Or using T for true, something like that. So if a proposition is false, its truth value is what? Is false. So the truth values true and false are respectively denoted by the letters T and F, or 1 or and 0 respective. So 1 for true, 0 for what? For false. But guys, for us, let's stick with the T for true and false for F, unless we are doing Boolean algebra. When we're doing Boolean algebra, we use 1 for true and 0 for what? For false. But for this propositional logic, please let's make use of T and F, right? Then let's talk about what we call a simple statement. There's what we call a simple statement and a compound statement, which means if something is simple, right? So a simple or a primitive statement is a statement which cannot be broken down into anything simpler, which means that's the simplest possible way we can express it. So a simple statement is denoted by the use of letters, the small letters P, Q, R, whatever, something like that. It doesn't mean that you can just say P, Q, R. It can be called S, but normally we use small letters for simple statements, and we normally write it or express it as P is such that, or a statement P is such that there are 7 days in a week. So this one is a statement. Why? Because we can approve it or disapprove it, and for sure there are 7 days in a week. Also, P is a simple statement such that so this one P is a simple statement. So this R is a simple statement that 3 plus 2 is equals to 6. Yes, this one is a statement. Why? Because we can approve it. We can prove it that is this true or not, right? Like here 3 plus 2 is equal to 5. No, it's not equal to 6. So this one is a statement, but its truth value is what? Is false. So these are more examples of statements, right? So from you guys, I want to know which ones are statements and which ones are not, right? Grass is green. Is this a statement or not? Let's talk about this. Grass is green. Grass is green. Not you, Fred. I want someone. Munashe Chua. Yes, you can admit yourself. Why saying so? Can you prove it or disapprove that the grass is green? Oh. Oh, Corey dry red green. So you see, so this one is, it's not a statement there. You cannot really prove it. This one you cannot really prove it. Mathematically, whatever, not, you cannot really prove it. So this one is not a statement at all. But what if you look at 4 plus 2 is equal to 6, you can really prove this. And this one is a what? Is a proposition. 4 plus 2 is equal to 6. This one you can prove it. There are 4 fingers in a hand. Yes, this one you can prove it. We can count how many do we have. So which means also this one. So this one is also correct. This one it's a proposition. Yes, grass is green. Yes. By mere looking at it, yes, you can prove it. Like when you say that you've always seen the grass as green, and if it is dry, it's not green. So it depends with what you have there, but I'm sure that you can prove this. This one you can prove that grass is green. It can either hold the truth value of either true or false, depends with the grass that we are talking about. For this one, I'm sure you can prove. This one you can prove. Yes, this one can either be true or false, because we are looking at something that we are holding. Whatever the grass is green, let's look at it. Is it green or not? Yes, based on colors, I'm sure this one. Yes, this one. It's sorry for that. You are correct there. This one is what is true. Then there are those like close the door. Really, it's not about is the door closed or not. You just say close the door. So this one, it's not a proposition at all. It's not a statement, right? If I say it's not a proposition, say we are saying it's not a statement, because we remember we've said that a proposition is a what? Is a statement. X is greater than 2. What about x greater than 2? Is this a proposition or not? Is this a statement or not? X is greater than 2. Let's talk about this. Ratio mgan. You can unmute yourself. Let's talk about this. Okay, maybe your mic is not working. Let me pick someone. Malvin, can admit yourself and contribute. Exactly. Exactly, that's it. So it's not a proposition, so it's not a statement there. Why? Because we do not know the value of x. But if you say 5 is greater than 2, then we can say this one holds a truth value of true or a truth value of false. But this one, we do not know it. So we only know whenever you substitute the variable there. Like this one, he's not, he's very rich. This one, it's not a proposition as well. He's very rich. uh, then understand both rich. What rich means to me is not what rich means to you, right? Ndokuti ndine $2, I feel like I'm very rich. Someone I need 10 cents feels like he's very rich or she's very rich, just because the past taught them this lesson, whatever, something like that. So we cannot say that he is very rich, and then we say this is a statement. No. So because to someone else, that person might not be rich, right? Unongotooneka ka 5k kako, but Elon Musk achitokuona anenge achiti usati watanga nditi. Okay, so let's look at these ones are more examples. X plus 2 is positive. This one as well is not a statement. Why? Because this x, we do not know what it is. May I come in? It's not a statement. This one, it's just a question there, but it's not a statement. It cannot be true or false. Logic is interesting. This one is a statement now, because it can hold a truth value of true or false. If I say logic is interesting, it's either true or false, right? It is hot today. This one, we can look at the temperature. Is it hot or not? Minus 1 is greater than 0. It's a statement. This one, it's not a statement. Now let's talk about the compound statements, right? So the simple statements, we said these are those that we cannot break further, right? Into any simpler terms. So the compound statement are those which are joined, right? So a compound or a composite statement is a statement which is comprised of simple statements and logical operations, or what we call logical connectives. So a compound statement is denoted by the use of letters P, Q, R. So if you look at that, now we are using the capital letters for those compound statements. So what do? We take those simple statements and join them to form what we call the compound statements. So for example, here there are 7 days in a week and 12 months in a year. This is a compound statement. Why? Because it is there's this first statement and joined with this second statement using this logical connective and. something like that. Then there's this there's so if you look at it, so we can let this the first statement be small letter p, the simpler. So this one need to be a simple statement, and this one's a simple statement that we've joined together using an AND operation. So the first one we can let that this one will be, there are 7 days in a week, so it's p, and then this one it will be q, the 12 months in a year, and then you can join them to make the compound statement p there, something like that. Here we have the grass is green and it is hot today, and we are joining it using what? Using it or to form this, the compound statement q, which says the grass is green or it is hot today, something like that. So we are using the logical connective or just like that. Also you can have them, maybe these three, joining them, right, like this. It is raining, I will go outside, I will eat my lunch, to form if it is not raining, then I will go outside and eat my lunch. So now we are using the if, then, and operations. These are the ones that we have used. So there's what you call a negation of a statement, like the negation of p, like if it is not raining, we are negating that it is raining. That's what we call the negation, something like that. So here it is saying determine. This one is an exercise to say if is this a simple statement. If it is not a simple statement, what was the operation that was used? I'm not going to look at that. It's an exercise for you. Then let's look at the logical operations or connectives. Normally the connective, if you are talking of a negation, the meaning is that it is not, we are, and then we normally using this tail, this symbol, this symbol. If you see this symbol, know that we are talking of a not operation or the negation operation. Then there's what we call a conjunction. A conjunction is an AND logical operation, and normally we use this symbol, this head. These are very, very important, guys. You need to know that, because the next thing that you are going to see is this symbol, not this AND. So you need to know what does it mean, and we talk about how do you use this operation. Then there's the disjunction, which is the OR, and it is represented by this symbol, which is some sort of a V. And then there's the conditional logical operation. The conditional is if then. When you say if this condition, then I will do this, and it is normally represented by this, the implication of this R. And then there's the biconditional, which is if and only if, right? That's the biconditional. It goes both directions, so you put the double R. So you really need to know all these symbols and what are their meanings, and which connective or which logical operation that we are talking about. Is it conditional? Is it biconditional? Is it disjunction? Is it conjunction? Is it negation? Boom, we are good to go. So for example, here I've got Harare is the capital of Zimbabwe, and the Q is simple statement. These are simple statements. So if we've got P as a simple statement, you say Harare is the capital of Zimbabwe, and the Q 18 is divisible by what? By 3. So if you say P and this symbol and a Q there, so you might be given this and asked to write P and Q in what? In words, right? So you'd be said, there are two statements, P, this, and Q, this. So please write in the words this statement that we have. So for you need to know that this is the AND connective. This one is the AND connective. So we are saying Harare is the capital of us of Zimbabwe, and 18 is divisible by 3, just like that. This one is P or Q. So Harare is the capital of Zimbabwe, or 18 is divisible by 3. Then this one is the negation or the not operation. So we are saying negation of P, this one. So it is not the case that Harare is the capital of Zimbabwe, or just simply say Harare is not the capital of Zimbabwe. That's the negation. But you're saying Harare is the capital of Zimbabwe. So the negation of that is that Harare is not the capital of Zimbabwe. Then let's talk about translation of translation from English to symbols. So sometimes you are given sentences to convert to symbols. Like here you've got let P be the statement it is hot, and Q be the statement it is sun. So now it will be written like it is not hot. Then what is its symbolic form? If you look at it, we are looking at P, that it is hot. So when you say it is not hot, now it's the negation of what? Of P, just like that. Then it is hot and sun. We use the and connective, so it will be P and Q. It is hot or sun. We use the or connectives. That's why we've got P or Q. It is not hot but sun. So because we have said it is not hot, it's the negation of P. But sun, it means at the same time it is not hot, at the same time it is sun. So it is not hot, which is negation of P and Q, like this, without the brackets here. It is neither hot nor sun, which means we need to negate it is not hot and it is not sun. That's the neither nor there, just like that. So that's how you convert from these English sentences to these. So it's very, very important to really look at these things. It's very, very important so that you sharpen yourself, right? Then there's this example in the practice that we have here, which says that we've got three statements, simple statements, which says Don is health, Don is what? Is wealth, and Don is wise. So you need to translate the compound statement to its symbolic form, and then you are given that Don is health and wealth, but not wise. So you might be given this. Then you want its equivalent symbolic form, right? So the first thing is Don is health and wealth, but not wise. So there is the negation of S here. That's why you are seeing H and W, then and the negation of S. The Don is not wealth, but he is health and wise. So the first thing is that you negate S. The Don is not wealth, so you negate W and H and S, something like that. Then Don is neither health, wealth, nor wise. So you negate everything and use the and connective. So if there are any questions, contributions, please do so. Let M be equal to Alex is good in mathematics, and C be equal to Alex is a computer science student. Then translate the following statement from translate the following statement forms into plain English. So if you say negation of C, which means it's negation of Alex is a computer science student, which means Alex is not a computer science student. So that's what you'll be doing there. C or M, Alex is good in mathematics, or Alex is a computer, something like that. Then M and the negation of C, Alex is good in math but not a computer science student. So a convenient method for analyzing a compound statement is to make a what we call a truth table for it. So there's what we call a truth table. You need to know about this truth table. So let's talk about these truth tables. What are these things that we call a truth table, right? So a statement P can hold one of two truth values, right, which is either true or false. So these are denoted by T and F respectively. T for true and F for false. I think I've already talked about this. And then some books may use 1 for true and 0 for false. And we said that we are going to use T for true and F for what? For false. So when determining the truth value of a compound statement, or possible combination of the truth values of the statements comprising it must be considered. So this is done systematically by the use of what we call truth tables. So therefore, a truth table specifies the truth value of a compound proposition for all possible truth values of its constituent propositions. So now let's look at how do you create what we call this truth table thing. So to construct a truth table, assign each statement a column. So like what we have been doing here, we have been having these statements, right? These symbolic statements. So these symbolic statements, you give each a column, right? And then the number of rows in the table is determined by the number of statements. How many statements do we have? Right? So if you have 3 statements like PQR, then it determines how many rows are we going to have in that truth table. So for any statements, 2 to the power n rows will be required. So if you have got 3 statements like PQR, small letter PQR, those simple statements, right? What do we do there? We say 2 to the power 3. So we're going to have 8 rows. Systematically assign truth values to each of the statements beginning in the first column. So you normally start with the first column. Once all possible truth values for the simple statements are inserted, then determine the truth values of the compound statements following the rules for the operations. So normally that's how you do it. And the way you assign the truth values, you use what you call the half rule, something like that. We look at it. So normally like here, this one is just the negation or the not whatever, which was put on a truth table there. And if you look at it, you are only dealing with a p, so it will be 2 to the power n. So we have only 2 rows, which will be 2 to the power 1. So we have these 2 rows, and then the first one it will be true, the second one we put false there, and then now we put the columns for the compound statements of the statement that we want to prove, something like that. So here we only want to deal with the negation of p. So whenever you have a truth value true there and you negate it, you get a false. So whenever you have a false and you negate it, you get a true. That's what this means that we have here, right? So that's the truth table of negation. Then there is this truth table of conjunction and, which is the truth table of an and logical connective or an and logical operation. What does this mean? So if P and Q are statements, then the conjunction of P and Q is P and Q, this one, and denoted by this in a symbolic form. So it is true when and only when both P and Q are true. What does this mean? Let's talk about it here. So guys, let's look at how do we construct this truth table. The first thing is we only have 2 simple statements, P and Q. That's why we've got it. So for P we put a column, for P we put a column, for what? For Q first. Then the next thing is how many rows are we going to have? Because we've got 2, it will be 2 to the power 2. So we're going to have 4 rows. That's why we've got 1, 2, 3, 4. Then after that, how do we assign now possible truth values for P and Q? That's when I said use the half rule, right? So because we've got 4 columns, so you first on the first column, you start on the first column. You can either start by false or by true, but normally it's always good to just start by trues there, right? So you write true until you reach the half of the number of rows that you have. So it's true. Then here we are now at the half of the number of rows, because we've got 4 rows. So you just write true, and then next you write false, just like that. And then what do you do now? On the next column or on the next simple statement, which is Q, now you do half of what we're doing here. So it will be now true, false. Why true, false? Because here we've got say true. So half of that, it will be only 1. So it will be true, false. So if there were 3, it means we are going to have 8 rows, right? So we are going to have maybe the first 4 rows, it was going to be true, then false, something like that. Then on the second here, it was supposed to be true, because it will be half of that. Then false, false, true, true, false, false, just like that. And then on the third one, it was just going to be true, false, true, false, true, false, true, false, something like that. And then here, this one is the result of the operation that you are doing, because this is what we want to do. This is the compound statement that we want to find its truth value using the truth table. So now what do? Now we are looking at the AND logic operation. So you say true and true. What do we get if it is true and true? So if both the statements are true and we are using the AND operation, then you get a true. But if any of them are false, you get a false. So true and false, you get a false. False and a true, you get a false. False and false, you get a false. So it is saying that when you're using the logical connective AND, it is only true when both inputs are what? Are true. Otherwise, it is false. That's what we are talking about here. Then there is the OR part. You know, when you are using an OR, like in programming, when you say if this or if this part or this part, you know that what happens is it executes that whenever one of the two is true, something like that. It just applies the same here with this OR, right? Whenever one of the input is true, then the output is also true, just like that. So it is true when at least one of P or Q is true, and is false only when both P and Q are false. So this is the truth table for P or Q. So true or true is true, true or false is true, false or true is true, but false or false is false. And then there is the exclusive disjunction. The exclusive disjunction. The exclusive disjunction is symbolized by this one. I think we've talked about this when we're removing the intersection, whatever, when you're doing the set theory, something like that. So the less than, greater than or equal to, less than or equal to, something like that. When you're removing those boundaries, that's when we'll be talking about the exclusive disjunction, something like that. So the compound proposition is true when exactly one, that is one or other, but not both of its components is true. So the truth table is that it is only true when we have different inputs there. Otherwise, when you have the same inputs, the result is false. That's what it is. Then what else do we want there? Let's talk about let's talk about the if then, the implication. Let's talk about the implication. If then implies, or what you call the implies statement. So also known as implication, consider the statement: if you earn an A in math, then I will buy you a computer. There's a condition there. If that condition is true, then we do whatever the implication, something like that. So this statement is made up of two similar statements like P, you earn an A in math, and Q, I will buy you a laptop. So we are saying if P, then Q. So normally we write it like this: P implies Q. Remember that diagram, not diagram, but that I think it's this one. Where is it? This one, right? We're talking about the conditional. This one, the if then, right? That's what we're talking about there. So remember about that. So that's how we write it, right? So you might see as if then, like if P is true, then Q is true, whatever. Or C is P implies Q, or B or C it being written this. Or maybe there are some of the terms that you might be see which are not those things. All right. So if P and Q are statement variables, so the condition of Q by P is if then P. So you can see maybe Q by P, or maybe P implies Q, which is denoted by this. It is only false when P is true and Q is false. That's when you get what? False there. Otherwise, you will always get a true. And we use this arrow operator there. Okay, so what it means is that here we use this truth table here to get this output. So we say true implies true, you get a true. True implies false, it's false. Hakuna ponese true value, then upon the false value, it's false. But you can have a false value there and implying what? True. False implying false is true. Having false there, you can get a false there, is true. So normally, this is what you get from this. So I don't know how you familiarize yourself with it, but that's what it is there. So normally other ways of expressing the implication are that if P then Q, P implies Q, or not P unless Q, right? Or Q follows from P, or if P Q, or Q if P, then Q only if P, sorry, P only if Q, something like that. Q whenever P. These are some of the terms that can be used to express the implication, right? So P is sufficient for Q, Q is necessary for P, something like that, all those things, right? Then what else? More about the given the conditional proposition P implies Q, we define the following: the converse. Okay, there's what you call the converse, the inverse, and the contrapositive. I think these things also are very, very important. The converse of a P implies Q, the inverse of P implies Q, the contrapositive of P implies Q. You need this when you're doing discrete mathematics as well. When you're doing proofs, we'll be asked to prove by contraposition, something like that. You need to understand these issues of contrapositive, something like that. You need to really understand those things. There's what you call a converse of the implication, and an inverse of the implication, and the contrapositive of the implication. So the converse of P implies Q, it will be just Q implies P. So it just interchange. The inverse of P implies Q, you negate this and you negate this. So it will be the negation of P implies the negation of Q. That's the inverse of it. Then the contrapositive of it, it will be now the negation. So you negate what you exchange the inverse, whatever. So it will be the negation of Q implies the negation of P, something like that. So this shows the truth values of the converse, the inverse, and the contrapositive. So how do we do this? Because we only have two statements, simple statements. If you look at it, we've got the P and Q. I was looking at the comments which are on YouTube to see if there are questions. Okay, but I think we are okay. So there's a P and Q there. That's why we've got true, true, false, false, true, false, true, false, true, false. Like we have these 4 rows. And then for P implies Q, which is the implication part, right? Then we are going to have true, false, true, true, like that. And then we look at what is it, the converse, right? The converse, which is Q implies P, which is going to be this. So how do you do this? How do you find this? Because it's the converse, it will be now Q implies P. So it's now true implies true, false implies true, something like that. That's how you get these values, right? So it will be only false when you say true implies for something like that here. And then we've got this, the inverse, and then we've got this, the contrapositive, something like that. So that's the truth table for that. And if you look at it, this and this are the same, which means the converse and the inverse are giving us the same output value there, or they are logically equivalent, something like that. So you'll be asked here as an exercise: state the converse, the inverse, and the contrapositive of the proposition. If Jack plays his guitar, then Sarah will sing. State the converse, the inverse, and the contrapositive of the contrapositive of the proposition. If it's not Sunday, then the supermarket is open until midnight. So this is an exercise. But guys, when I look at the converse, the inverse, and the contrapositive, you are looking at these 3 things here that we have write in a symbolic form. Okay, so someone to tell me the converse. If Jack plays his guitar, then Sarah will sing. What is this converse? What is the converse there? Someone to try. I think it's the simplest one. I think it's the simplest one. There's a hand by Wilfred. You can try Wilfred, being given that the converse is this one. You never have P implies Q, we have Q implies P. So we have, yes. So in English terms, how do we say it? Yes, Sarah will sing if Jack plays guitar, or if Sarah sing, then Jack will play his guitar. It's like you are just exchanging, right? So like here, so that's how you write it, right? So you need to define what is P, what is Q. So the converse of it, it will be now if Sarah will sing, then Jack plays his guitar. The inverse of it now, so symbolically this is the inverse of it. So now you need to look at what is the negation of P. The negation of what? Of Q, sorry. So it is Sarah will sing, which means Sarah will not sing. So because we've got the implication, so if Jack doesn't play his guitar, then Sarah won't sing, something like that. So it will be negation of P implies the negation of Q. Then the contrapositive is the negation of Q implies the negation of P, right? So if Sarah won't sing, then Jack doesn't play his guitar. So you just need to really know what is the converse, what is the inverse, what is the contrapositive of a given statement. So if you are given a compound statement, how do you break it into its simpler terms, and how do you give these English statements from this whatever symbolic form of those converse, inverse, and contrapositive? I think it's something that we can really do. I think it's something that we can really do. And then this the inverse of the condition or of a conditional statement P implies Q is this, and the conditional and its inverse are not equivalent, as could be seen. Okay, we are just saying that the statement and its inverse, they are not equal. And you can look at here for true, false, true, true. But here we've got a true, here we've got a true and false, true. So this and this are not equal, this and this are not equal. Hence, a statement and its inverse will not give you the same answer there. Then there is the by conditional, which is the if and only if. Excuse me. So whenever I see if and only if, please think of this, right? Which is the bi-directional or the bi-conditional. So if P and Q are statements variables, the biconditional of P and Q is P if and only if Q, and it is denoted by P implies, or this one symbol here, Q is not the implication, but P if and only if Q, this one. So if and only if is abbreviated by IFF. So if you see this, know that it's if and only if. So the double-headed arrow, this one is the biconditional operator. So normally this will be the truth values here. It is only true when both values are of the same, or both inputs are of the same. If you have got a true true, it will give you a true, but if you have a true false or a false true, there it will be false. It is only true when you have both a false or both truths. Agreed. So if and all, the alternative wording for P if and only if Q can be P if and only if Q like this, or P if and only if Q, or P implies and is implied by Q, or P is equivalent to Q, or P is a necessary and sufficient condition for Q, something like that. Then order of logical operations, do we really need to look at this? No, we do not need to look at this. So maybe we need to really look at what is a statement, maybe how a compound statement is formed. This is just a summary of what we have looked at. Logical connectives, the negation, the conjunction, the disjunction, whatever that we've looked at, the end, those are that's the conjunction, and the disjunction is oral, and maybe those the implication, the bicondition, the biconditional, how to construct the truth table. That's what we have been looking at. Then there's what we call a tautology here. There's what we call a tautology. It's very, very important. These key things that we'll be talking about. What is this thing that we call a tautology? That's what you really need to know. And you'll be able to actually construct the truth table already. So a tautology is a statement form that is always true regardless of the truth values of the statement variables. So whatever we give as the values of the statement variable, what we always get is a truth value here under that statement. So we call that statement, it's a tautology, right? Is that a contribution or a question? Okay, so let's try to always be on mute. Okay, so the statement for form P or negation of P is a tautology. Why so? Because we are only dealing with the P, so we are going to have true, false there, and we are going to have two rows just like that. And then negation of P, so we're just negating this one, negating this, we get a false, we get a what? Here we get a true. Why are we putting this column? Because we want to find P or negation of Q. So now it will be easier. We'll be now saying P or negation of Q. And you know what we have always said, that for an oral, if these ones are different, we always get a true. So P or negation of Q, which is true or a false, we are going to get a true. False or a true, you are going to get a true there. So because all these values are true, it means this statement is a what? Is a tautology. Then there's what we call a contradiction. What is this thing that we call a contradiction? This is very important, especially when you are doing discrete mathematics. You'll be asked to prove by contradiction. So this is really important. So a contradiction is a statement form that is always false regardless of the truth values of the statement variables. So it's some sort of like opposite to the tautology, right? So it is always false. So a contradiction is represented by the symbol C normal, and therefore, so if we have a proof that a given statement form is contradiction, we will make the truth table for the statement form, and if in the column of the given statement form all the entries are F, then say that the statement form is what? Is contradiction. For example, the statement P and negation of P is contradiction. Why? Because if you look at it, we are getting this false. So we can say that this is a contradiction. This statement is a what? Is a form of a contradiction. So these are some of the remarks that we have. I'm not going to go through this. Then the logical equivalence. Two compound propositions are called logically equivalent if only if they have the same truth values, no matter what truth table truth value their constituent proposition they have. So if they always have the same values, we can say these are logically equivalent. Like to say P plus Q is logically equivalent to negation of P or Q. What we'll be looking at, you look at this column, right, and this column. Why? Because this is what is under consideration. Is it P implies Q and this is it the same, right? So the first thing was to have P and Q there, whatever you put the inputs there, and then you find the negation of P. Why? Because we want to use it here, so it will be easier, because we'll be saying negation of P or Q. So you'll be saying negation of P or Q, something like that. So negation of P, yes, or Q, this one. So it will be true or false, something like so. You'll be having something to compare with, rather than to say negation of P when you do not have the negation of P. So you want to start by flipping this, and then you say or, so you be saying false or Q. Then you come here, you need to flip this to false, then you say or false. You come here, you need to flip this. So it's good to just have the separate column where you flip everything for P and then now you work with this just like that. So if you look at that, here we've got a true, here we've got a false, here we've got, so these are the critical columns that here is true. So these are logically what are logically equivalent. Then what else? I think for this one, the laws of logic, let's leave it. This one I'll leave it to your lecturer who is going to take you on discrete mathematics. That's where you are going to do all those whatever, the De Morgan's laws, the implication laws, whatever, where you'll be simplifying that. But I think for what we need for propositional logic, we've covered everything. We've covered everything that we need. Maybe for this 8 minutes, let me see if I can just quickly try to go through the, not the predicates. For predicates, allow me to jump that. Allow me to jump that for good reason. But I think there's a video that I've put on YouTube as well, which explains predicates, what are predicates, whatever, how do you go about that. Please take note that it is very, very important as well to just go through them, or to just go through that video to grasp the concept, what are predicates, whatever, something like that, so that you just really know that, because it's a very, very topic that you might find as well when you're doing discrete mathematics. Okay, so let's look at the Boolean algebra, right? So there's what we call combinatorial what circuits. So this is a circuit. There's a repetition here, whose output is uniquely defined by its what, by its input. So they do not have a memory, so they do not know the previous inputs, or the previous inputs do not affect their output. Some combinations of gates can be used to make more complicated combinatorial what circuits. So here there is these gates that we normally use, the AND gate. Let me have there is what you call the AND gate, not a highlighter, but I need I need a highlighter, not a pen. So there is this AND gate, the NOR gate, the NOT gate, the NAND gate, and the OR gate. Normally that's how you draw these gates, right? And remember, when we're doing propositional logic, we're talking about the AND logical connective. It's just the same with this one. It's just the AND that we're talking about. So the truth values that we're talking about, they also apply here, but only that here be normally using 1 and a 0. So the NOR gate, it's not OR. So when we were doing the negation there, right, like the negation that we used to do, where we are flipping something like that, so the not or there is the combination now of the not gate and the or. The not is the negation where we'll be flipping something like that, so this will be now a combination. Then the NAND is a combination of not and, right? So we have the negation and the and get something like that. So it will be it will have this circle and this shape of end. This one is just the not, this one is just the OR gate. So the truth table now, or the logic table, we normally call it the logic table. For a gate, we normally use the ones and the zeros, but the way of drawing them is just the same like what we've did here. We have got the x1 and x2 as inputs, right? That's why I've got 4 rows, and that's why if you look at, we've got true, then false, or 1 1 0 0, and then here it is 1 0 1 0 1 0, something like that. And then whenever you see x1 plus x2, normally here we use a plus for an OR gate, so we are working with this OR gate. And whenever you are working with an OR, you know what happens? It is only false whenever both inputs are false, right? So here it's as good as x1 plus x1. So here it's just x1 plus x1, something like that. It's only that they were squeezed. That's why it's something is the top and then this one is below. So it's below the plus. So whenever both inputs are true or are ones, here we have a 1. Whenever we have n of them being 1, here we have a 1. It is only false when both inputs are false. take it like what you do with the if statements, whatever. Take it like what you have been doing with the oral logical connective, something like that. That's if you take this truth table, you see that with what we are doing is just the same. And then when you are using this dot, we are using the end, so we are dealing with the end gate, right? So when you are using an end, like what you have been doing, it is only true when both inputs are what are ones. Otherwise, it will be zero. So it will be 1 times 0, 0, or 0 times 0 times 1 is 0, 0 times 0 is 0, something like that. But what it is that it is only true when both inputs are ones or are true. Then there is the X bar or the negation, which is this symbol, this one. We are just flipping the input. So if there's a 0 there, you flip it to 1. If there's a 1, you flip it to a 0. And then there is, now when we have this gates being drawn here, how do you find this output or the expression here at the end, something like that. So for instance, fig 7.2, I'm trying to manage my time there. For instance, figure 7.2 is a combinatorial circuit with the logic table shown below representing the values of the Boolean expression. So if you look at it, we've got the AND gate here. So there is, this one is A and B, that's why there's A dot B there. Then we are flipping the result that we get, that's why there is a bar there. And then we are multiply, that's there is this dot here, because this one is the AND gate, with whatever which is coming from this. What is coming from this side? If you look at it, we've got an A which is and a B which is going inside the OR gate. So it's A plus B or the A or B, right? So we write it as plus when you are doing Boolean algebra, right? So it will be A plus B, but there is the not here. So we are flipping that. So we are putting a bar at the top, and then we are multiplying it with whatever which is coming from this side, which is this one times this one. So you might be asked to draw this, right? So when you're given this, you'll be asked to come up with this diagram, or you'll be asked to give the outcome. What is the expression for the outcome, which is this one again? By just given this, you need to know like what how I drive to come up or to end up with this y or with this output, right? Or to come up with the truth table for this logic gate. So now, like what we did when we were doing all the truth tables, like here, this one is just a shorthand there. So I've got x1, x2 there, and maybe x3 there. What is x3 there? Let's look at this. Maybe it was simplified. What do we have here? Y is it was a dot b, then bar plus a, then bar a plus b. Okay, so this one, it was this was some kind of it was a simplified x1 there with 1 whatever x, because we've got 3. This one was simplified, but I think it's better to really try to come up with this. I think the best and the easiest way is to come up with this as it is, this one, where you could maybe break it as this one to have A and B, then you do the bar of that, and then you also do A or B, then you do the negation of it, and then you just do those 2 columns to give the output. What I'm sure is you get this. This is what you will get there, and that's the simplest way than to try to reduce that. But at the end, what you get, it is this, and what you'll be using is just those, the end or whatever, something like that. Because if you look at it, this one, it was x plus 2, which was this one or this one, and then you do the end of that result, and then what you do is you flip that result, or you are doing it in your head, and then you put the final end result, which is not the good way to do it. And then for this one, I think we do not really to look at all these things, equal Boolean expressions. For these ones, you can just maybe have a mere look at it or to skip it. Otherwise, for today, I have the basics that I really want to cover. What I will do is I would ask if there are questions before I rush home. I would ask if there are questions before I rush home. Before we call it a day, or contributions as well, or contributions, questions or contributions. People do not want to talk, and I'm not going to ask. Otherwise, I would ask so that you would talk. But otherwise, guys, okay, Valence, you want to say something? You can unmute yourself. Can unmute yourself. Okay. Okay. Okay, I think I've explained on that it was reduced. So the best way to do it is better to work with A and B there. And how do you do it? You just do like what you've been doing when you're doing the propositional uh, logic, where we're looking at those truth tables. If you look at it, just a matter of expanding it to say A and B, then you do the column for A and B, and then you do for A or B, and then you negate A and B. So it's just one column for negation. Then you negate A or B. It's just one column, and then after that, now it will be simpler. You are now working with the two columns, the negation of A and B and the negation of A or B. So you multiply them. So you are now using the AND operator, not to multiply, but you are now using the AND operator. Then you get your result. Just as simple as that. Then try to go through the way of reducing it. Exactly. You are welcome. I don't know if there are any questions or contributions. Okay, so if there are no questions or contributions, someone was asking on YouTube, will it be wrong if one creates the inputs in ascending order from zero going up instead of going down to zero? I think I didn't get the question in right time, so it's really kind of hard for me to link it to maybe to what you were asking. Like you said, of if I don't know really. Okay, so there's a hand by Vengai. There's a hand by Vengai. Yes, Vengai. Go on. Mm-hmm. To the slides. Okay, let me unshare my screen so that I will navigate through. Was I already closed the folder and what? Okay, so I will just unshare and reshare uh, when I'm okay. Let's let me share my screen. For if then, why the implication? it, it yeah, this one. Okay, that's what I said. It is what it is. Normally, if the input is false, you are likely to get a false, right? So if it is false, then Q is what is false. And then there is now this part which says if the input is false, then it implies that Q is true. So what happens here is that when you look at this input false and then this output as true, normally we say that this false that we have given here, right? We say it to be false. But here it is giving us a truth value, which means this thing that we say is to be false, it's actually what? It's actually true, something like that. So it's as good as we are giving a false input there and getting the what? The true output there. What it really means is that the result is what? Is true. If you are getting a true out of what? Out of this false, then what means this one is what? Is true. Then here, if you are giving a false value and getting a false value, it means it is true. Is that making sense? We are giving a false value and we are getting a false value, which means it is true. That if you are giving a false value, you are getting a false value, so it is true. This one, you are giving you are giving it a false value, right? Then it is giving you what? True. So what it means is that this statement is what? The original whatever is what is true. So maybe you can just go and read around it, play around it. You find the funny part around it. That's why I've said that it is what it is. And this is the correct part. It is correct like what it is. So you try to make whatever way you are going to infer to it to make sure that you really get the concept there. Yes, Marvin, you want to say something? Marvin, you want to say something? Hmm? Well, what's your question? I'm not getting it. Okay. Okay. It's okay. You are a little bit low. That's the issue.
to go back again. But I have an idea. I got the slightly but thank you so much, sir.
Oh, okay. So I don't know if there are any other questions or contributions um before I go. I think everyone is now satisfied. So maybe guys, what we can do is maybe we can talk later on the group what we need to do next. But otherwise, have a good night.
Thank you, sir.
You're welcome. You're welcome.